Welcome to the sixth lecture in Applied Math. The topics that we will explore in this lecture include inversion centers, improper rotations, and assigning molecules to point groups.
Okay, so we'll start with the exercises from the previous lecture. So first, let phi be a map from the integers into the set of integers modulo n, and let this map be defined by phi of a is a modulo n. Then this map phi is a homomorphism but is not an isomorphism. So proof, let a and b be two integers. Then phi of a plus b is a plus b modulo n, and this is the same as a modulo n plus b modulo n, which is phi of a plus phi of b modulo n, and hence the function phi is a homomorphism Now, since the cardinality of the set of integers is aleph null, that is, there is a countably infinite number of integers, and the cardinality of the set of integers modulo n is the finite number n, we have that the cardinality of the integers is not equal to the cardinality of the integers modulo n, and so there does not exist a bijection mapping the integers onto the integers modulo n, and hence the function phi is not an isomorphism. So next, let n be a given integer not equal to 0, and let the set n times z be the set of all integer multiples of the given integer n. Then the function phi mapping the integers into this set is defined by phi of a is equal to n times a is an isomorphism. So proof, let a and b be two integers. Then phi of a plus b is n times the quantity a plus b, which is n times a plus n times b, which is phi of a plus phi of b, and hence the function phi is a homomorphism Now suppose that phi of A is equal to phi of B. Then n times A is the same as n times B. And since n is not equal to 0, we have that A is equal to B. And hence the function phi is an injection Now for every element B in the set n times z, B is equal to n times A for some integer A. That is, for every element B in the set nz, there exists at least one element A in the set of integers such that B is equal to phi of A and hence the function phi is a surjection. So as phi is both an injection and a surjection, it is a bijection, and we have already demonstrated that it is an isomorphism, that it is a homomorphism, and therefore the function phi mapping the integers into the set nz is an isomorphism, and hence the set of integers under addition, or the group of integers under addition, is isomorphic to the set of integer multiples of a given integer n under addition for every integer n where n is not equal to 0. Okay, so next we will look at the symmetry elements in a molecule of methane. Now the methane molecule has a tetrahedral geometry, and so the principal axis of rotation is a C3 axis, and there are 4 of these, one for each of the hydrogen-carbon bonds. Now this molecule also has some C2 axes, and these are somewhat more difficult to see. But notice in the model that if we rotate by 180 degrees, then we have an identical molecule. And there are 3 C2 axes. So we have 4 C3 axes and 3 C2 axes. So let's look at a slightly different orientation of the molecule. Now notice we have a plane that contains 2 of the hydrogens and the central carbon atom. And this plane is a mirror plane. Also notice that this plane, which again contains any 2 of the hydrogen atoms and the central carbon atom, also bisects two of the C2 axes. And so this is a dihedral mirror plane. Again, notice that each dihedral mirror plane contains two hydrogen atoms plus the central carbon atom. So determining the number of dihedral planes is a simple counting problem. So let's number the hydrogens: 1, 2, 3, and 4. So we have a mirror plane that contains the hydrogens 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and finally 3 and 4. And so we have 6 dihedral mirror planes in a methane molecule. Okay, so new definition. Let X be a subset of an n-dimensional real space, and let the point P in the set X be a specified point. And inversion in the point P, or a reflection through the point P, is a transformation which we will call phi, mapping the set X back into itself such that phi of P is equal to P, that is, the point P is fixed, and for every 2 points, X and Y, in the set X, the distance between the points X and Y is the same as the distance between the points phi of X and phi of Y. Now, a map which preserves distances is called an isometry. And so an inversion in a point P, or reflection through the point P, is an isometric transformation that leaves the point P fixed. So notice that in this abstract definition of inversion in a point or reflection through a point, that the identity map qualifies as a reflection through the point. Now, in three-dimensional real space, the term inversion generally means reflection through the origin, in which case the point x, y, z is mapped onto the point negative x, negative y, negative z. Now, a molecule is said to have an inversion center if reflection through the center of the molecule results in an identical molecule. So let's look at some examples. If we look at the carbon dioxide molecule, and we'll label the oxygens 1 and 2. The center of the molecule is the center of the carbon atom, and I'll indicate inversion by a lowercase letter I. Then when we invert this molecule, the oxygens have traded places, the pi bonds have traded places, but we still have an identical molecule. And so the center of the carbon atom in the carbon dioxide molecule is an inversion center. Now let's look at the methane molecule. And let's label the hydrogens 1, 2, 3, and 4. If we invert this molecule, then we do not have an identical molecule. And so a molecule with a tetrahedral geometry does not have an inversion center. So let's look at a few more examples. So let's look at two isomers of an organic molecule. So first, we'll look at the cis 1,2-dichloroethene molecule. Let's label the chlorine, carbon, and hydrogen atoms. If we invert this molecule, then we do not have an identical molecule. And so the cis 1,2-dichloroethene molecule does not have an inversion center. So now let's look at the trans 1,2-dichloroethene molecule. And again, we'll label the hydrogen, carbon, and chlorine molecules. If we invert this molecule, then we do have an identical molecule, and so the center of this molecule, which is the center of the pi bond, is an inversion center.